I would like also to thank organizers for inviting me. My talk is not going to be on a Koopman's method, but hopefully it will show that introducing some classical like variables in quantum dynamics helps to solve some problems with conical intersections and other kind of divergences. And let me start with motivating. Why do we want to study non-adiabatic dynamics and what sort of processes we're interested in? So a simple example is like a human vision. And it happens because, well, there is an isomerization involving multiple electronic states. And so from that example, you can easily imagine what the life would be without non-adiabatic processes. For that, you just need to close your eyes and it will be dark. So nothing really will be visible. So that is life without non-adiabatic dynamics. It's very important for the vision process. And then we also know that too much light could be dangerous, and turns out that non-adiabatic processes actually helps us to avoid damage of our DNA from light. And we can use transitions between electronic states to harvest light energy from sun and transfer it into a charge transfer so that we can use in batteries. So the processes that we're interested in studying, besides being non-adiabatic, we would like them to be relatively fast because like longer processes, they also can be non-adiabatic, but they are much harder to consider. So in this talk, we'll mostly look into fast processes. And another thing that, another feature that we are particularly interested in is describing nuclei quantum mechanically. So with that, the problem can be formulated for closed systems as just solving the time-dependent Schrödinger equation. And for this talk, I will be denoting small r's as electronic variables, big r's as nuclear variables. So the way to consider this problem, and the usual way chemists do it, is they consider the partitioning of the Hamiltonian into essentially electronic part, while grouping the electronic kinetic energy and the Coulomb interaction of all particles, leaving the nuclear kinetic energy as an addition. And that's a usual Born-Oppenheimer separation. Then if we want to study things from first principles, it's useful to solve the electronic Hamiltonian eigenvalue problem. And then using the eigenvalues and eigen vectors or eigenstates, the electronic functions, we can construct a total full quantum wave function, right? And this can be contrasted to quantum classical approaches where there is no quantum nuclear wave function like surface hopping or Ehrenfest. The distinct feature is that we don't have the nuclear dependence and they don't have nuclear wave function. Instead, we substitute the nuclear variable to our essentially classical trajectory. Okay, and we will be mostly interested in doing the full quantum dynamics with nuclear wave function. It's important to emphasize because in some of the methods that we'll be talking about, we use Gaussians that not necessarily moving quantum mechanically. They can move classically, but since they are still going to be a wave representing a nuclear wave function, the method is still going to be a quantum or full quantum. Now, one may wonder, why do we want kind of full quantum consideration for nuclei, even though the nuclei can be in many cases treated classically, or like the full formalism could be mixed quantum classical, like we saw some really great examples of Ehrenfest and surface hopping treating problems quite well. So there are a few still problems with the classical nuclei. One is that there is a problem with treating the decoherence in mixed quantum classical methods. Say, for example, in order to describe the Marcus rates, it turns out that it's crucial to consider the decoherence. Otherwise, you're going to get wrong scaling. Hopefully, we'll hear more about decoherence from Ignacio Franco talk tomorrow, but it's a problem for quantum classical methods. Another problem even in excited state dynamics, you would like to account for the 0-point energy and possibility for tunneling. Otherwise, the rates may be quite underestimated. And turns out that there are other quantum effects related to, in particular, the crossing of the potential energy surfaces, say the geometric phase effects that I will be describing in a moment in more details. It turns out that they also won't be treated properly if you switch to classical nuclei. So if you want to consider things from first principles and account for all these effects, then you need to kind of stick to the quantum nuclei. Even though there are some interesting recent reviews on how to incorporate those effects in classical methods. For people who are interested, please follow the reference below. Now, our approach is to consider this full wave function as a Born-Juan expansion. One reason why we would like to have electronic functions close to the adiabatic ones, the ones that are coming from the electronic structure problem, is because we would like to make a first principle consideration, meaning that we don't want any empirical kind of data or potential fitting. So we want to obtain things on the fly. And because we want to do things on the fly, we cannot really study the potential energy surface too much in advance. And natural nuclear representation is a linear combination of Gaussians, because Gaussians are relatively compact. And so we need only to consider electronic structure problem in the vicinity of the Gaussian center. So the way it works is that essentially the nuclear wave function in every electronic state is represented as a linear combination where the coefficients are time dependent. And then we have position and momentum of each Gaussian as a classical variable that changes with time. And the Gaussians are moving, and you can describe essentially the nuclear dynamics as moving Gaussian dynamics. Now, how do we obtain the kind of equations for these parameters of the Gaussian wave packet? It's by putting them back into the time-dependent Schrödinger equation. Of course, because the ansatz for your wave function is finite, the left-hand side and right-hand side is not equal anymore to each other. So in order to obtain the equations, it turns out you can just simply minimize the norm of the difference, right? So that gives rise to various time-dependent variational principles, because you're trying to vary the functions of, say, coefficients, position, and momentum of Gaussians to minimize the difference between the left-hand side and right-hand side. And it gives rise to like a system of differential equations that can be solved. Now, there are lots of people who contributed to this field. We're not the first ones who thought about this, of course, and some of them in the audience. And there are lots of ways to kind of formulate these equations, also because you have a choice to treat some of the parameters like, so you can actually make Gaussians move classically. That has a certain advantage because the classical equations of motions are easy to consider, but then the coefficients will be still treated quantum mechanically, and the whole formalism will be quantum mechanical. Now, in order to see like a certain systematic trends in how this whole approach can work in various areas, we wrote this kind of a small review paper where we provided the following framework essentially for all frozen Gaussian, at least, methods for non-adiabatic dynamics. And the key elements here is that you can vary how your frozen width Gaussians are moving. Are they moving classically, maybe using Ehrenfest or quantum mechanical equations of motion? Then you can also look at whether you want to have a finite number of Gaussians at all time, or you want to extend, spawn new Gaussians, or clone some of the Gaussians on different electronic states. And then the electronic representation can be also chosen in different ways. So all that is practically the same framework. It's just the different schemes, like multiple spawning has certain choices along like these three coordinates. Okay, and in this talk, I'm particularly, as I said already, that we're interested in sticking close to the electronic structure. Essentially, we would like the electronic wave functions come from the packages for the on-fly dynamics. And that's why we will discuss what are the problems with that approach. It's like using adiabatic representation. And these problems appear mainly when we have conical intersections. And then I'll tell you how all these problems can be solved by the new so-called moving crude adiabatic representation that we suggested. All right, so what do we know about adiabatic representation? This Born-Juan expansion, the wave functions are coming from the electronic structure problem, and it gives rise to many nice properties, like chemists like to draw these surfaces. They are potential energy eigenvalues that are parametrically dependent on the nuclear structure, right? So you can understand many properties or many processes using those surfaces. This is unambiguously defined in contrast to, say, diabatic representation, and can be obtained on the kind of relatively regular basis from the electronic structure codes like Gaussian or Koopman. So it's quite easy. Now, these potential energy surfaces are well separated usually, and the couplings, if those surfaces come close to each other, they're coupled, but the couplings are somewhat localized in the configurational space of nuclei. Now, the downside of the whole representation is that when surfaces actually come close to each other or intersect even, very frequently they intersect in this conical shape. There are maybe reasons for that. We can discuss it later, but this is what is actually happening. Then there are lots of difficulties appearing in the nuclear treatment in those cases of conical intersections. Now, one problem is related to non-adiabatic couplings. And those couplings are happening because essentially when we go back to the full problem, the entire Hamiltonian also contains the kinetic energy of nuclei. And we need to remember that the basis for electronic part of the problem we've chosen, it depends on the nuclear coordinates. And so the kinetic energy of nuclei, it's a differential operator. It will differentiate not only the nuclear part, but the electronic part as well. Now, that gives rise to certain terms. And these terms, well, although simply looking, it's kind of natural to see these derivatives respect to nuclear coordinates. But the caveat here is that it can be shown easily that essentially they scale as 1 over gap and 1 over gap squared. So where the gap is the energy difference between the electronic states. Naturally, when you come close to a conical intersection, there are divergences in those terms. And these divergences essentially create problems for your differential equations that you can formulate on the nuclear part of your wave function, right? And these problems naturally are coming, they can be traced to the nuclear dependence of the electronic states. So in a sense that the electronic states depend on nuclear coordinates, that helps us to kind of maybe select the electronic states which are just a few to represent the physics of the problem, but they also have a downside because they generate these non-adiabatic couplings. Another problem with this also that is coming from the nuclear dependence of electronic functions is so-called geometric, like appearance of geometric phase, when we consider the cases where the potential energy surfaces have degeneracy points. And so this was first found by Longe-Higgins, and then later Michael Berry generalized this for other cases, not only for the molecular systems. And so what we call geometric phase is also called Berry phase or topological phase. And probably in the cases of conical intersection, it should be really called topological phase because it's only plus minus 1 essentially, or change by pi, rather than a change that depends on the contour that you are using to go around the conical intersection. But essentially, the effect is that if you have any eigenvalue problem that parametrically depends on some parameter, you go around with any eigenvector of that problem of point of degeneracy, when you come to the same point, the eigenvector changes the sign. So, and there is a way to do this experiment, of course. It doesn't mean that if you use computer and to calculate a bunch of points, return to the same nuclear geometric point, your computer will give you like a different sign on the answer for your eigenvector. You actually need to connect the points and make sure that the phases are well aligned when you do this experiment. Then you can see that there is a change of the sign when you go around the intersection. And also this can be used to detect that you have conical intersection somewhere in the configurational space. But mathematically speaking, what this means is that electronic functions as double-valued object with respect to the nuclear coordinate. Okay, and in order to make the total wave function a single-valued object, what this means is that both electronic function and nuclear wave function must be a double-valued object. And we have some details described in this mini review, what kind of effects that kind of double-valuedness produce. So here, just to showcase few striking differences when you account and when you don't account for the double-valuedness. One big effect that you can see is if you look at the charge transfer processes in the situations where well corresponding to charge being on one side of the molecule is separated from the well where charge is on another side of the molecule by their like this two transition states around the conical intersection, right? Then your nuclear wave function really doesn't go around the conical intersection, but what happens is that in quantum mechanics, we have tunneling, and that tunneling happens on both sides of conical intersection. And essentially, the parts that are going from one side and another side acquire different in sign geometric phases or topological phases. And so what happens is if you account for that buildup of the phase, then the donor population versus time is pretty much negligibly changes. And so your wave function stays, or your system stays in one well. And if you don't account for that, then naturally you have a, like in any double well problem, you have a tunneling and coherent oscillations back and forth between the two wells. So we call this type of systems molecular topological insulators, because topology is responsible for insulating property and the charge transfer, essentially freezing. Now, it turns out that in photochemical events, this is also important factor, the geometric phase, because when you have a photochemistry event where you have your system on, let's say, upper state and it goes to the lower state, then you need to really account for these couplings. Otherwise, the system cannot really go from one state to another. And those couplings really looking into how the electronic function depends on the nuclear coordinates. And if you have double-valued or single-valued object, which here for some model system I represented here two coordinates, and so for this model system, there is electronic function behavior. You can easily imagine that the behavior is quite different, and then the non-adiabatic couplings are behaving quite differently in the two situations. So now, if you look at again the population dynamics now from the upper state to the lower state, you can see that going from, like, say 100% on the upper state, we go in time quite differently in time, depending on whether we introduce the geometric phase. Full here red curve is with everything, and if you kind of remove the geometric phase, then the transfer is just slower. Turns out that actually various quantum classical methods like surface hopping and Ehrenfest perform quite well in this case, and they reproduce quite well full quantum dynamics, even though they don't really include the geometric phase. So there are some reasons for the cancellation of errors that we discussed in the paper below. But returning back to Gaussians in our program, that we would like to put all these effects of non-adiabatic couplings and geometric phase, because they're all important. How do we do that using Gaussians for the nuclear wave function? Well, the bad news is Gaussians are single valued, and our electronic wave functions are double valued if you have a conical intersection in your problem. And if you want to do on the fly, you don't know upfront whether you have a conical intersection, maybe it's avoided crossing. So that's but you have then a dangerous situation that your nuclear wave function doesn't have a right boundary conditions. Okay, so what do we do about that? Now, if we return a step back a little bit and realize, okay, well, all our problems are happening because of nuclear dependence in the electronic wave function. So how can we change that? The kind of conventional approach to that problem is let's just try to reduce this nuclear dependence. It's like diabatic representation is one way to go. But it turns out you don't need to go to diabatic representation. Or kind of specifically, but what you can do in these problems is just you need to do a small tweak that is changing the nuclear dependence in electronic functions to a dependence on the center of the nuclear wave function, Gaussian in this sense. Okay, so here is it's a quite specific setup where for the nuclear wave function we use Gaussians, and Gaussians has centers, right? And centers of the Gaussians are not the nuclear coordinates; they are different entities. So if we just calculate electronic basis functions, not everywhere, even though it's practically almost impossible to calculate them everywhere, but just we specifically calculate them on the center. And use that for the Gaussian corresponding to that electronic basis function. Then it turns out that many of the problems I just talked about, they're just going away. Now, why did we call this moving crude adiabatic? Because crude adiabatic representation is a representation where you calculate electronic states using electronic structure, but in one single point. Because if you use the complete basis set, it's enough, but it's impractical, of course, because you cannot use complete basis set in real problems. So this is a crude adiabatic part. Moving part is naturally coming because the center of the Gaussian is moving. So it is like it's like crude adiabatic, but it's moving. So it's moving crude adiabatic. All right. So now how? Okay, just a little bit of emphasis on the difference between nuclear coordinate and the center of the Gaussian is that it's a lot like this transition which we do when we teach quantum mechanics. Because in classical mechanics, we have a nuclear, or like any particle coordinate as a function of time. It's dependent on time. At least we can think of Lagrangian frame if you'd like. And then in the quantum mechanics, we have an independent variable R, which is well, it's an extra variable, and this transition could be unnoticed, but it's important. Now, when we go to the center of the Gaussian coordinate instead of the nuclear coordinate, then we kind of introduce in a new coordinate, which is classical-like. Or if you want, you can think of it as we substitute a Euler frame nuclear coordinates by Lagrange type of frame coordinates of the center of Gaussian. All right, so what's the kind of difference between these two representations from the kind of practical perspective first? So practically, electronic problem will not even notice the difference between the two kind of representations, because we just need to solve the kind of the problem for the electronic Hamiltonian when we fix the structure of the molecule. So there's no difference really, whether that structure comes as a center of Gaussian or it comes from some discrete grid of points on nuclear space. Now for the nuclear problem, there is a big difference, because now the only nuclear dependence we have in our ansatz is in the Gaussian, and our electronic functions do not depend on the nuclear coordinates anymore. So the effect of that is actually quite tremendous, because now if we're talking about couplings between two electronic states, we don't have any more coupling because of the nuclear kinetic energy operator. It's a differential operator with respect to big R, but the electronic function doesn't have big R coordinates anymore. So the only non-adiabatic couplings we have, it's from the time derivative. It's like in the surface hopping and other quantum classical methods. where we differentiate with respect to time. According to chain rule, you need to differentiate on whatever you have an electronic function that depends on time, and that is the center of the Gaussian. The nice thing about this is that we only have, because it's a first derivative with respect to time, we only have first derivative non-adiabatic couplings, and those have like a lower degree divergence. It's like 1 over gap instead of 1 over gap squared, and they can be integrated. More than that, there is a nice feature here is that center of the Gaussian, it's a point, and like for the at least a 2D case, it's easy to see that one point will never hit another point, and by another point I mean conical intersection point. In 2D, it's a point, right? And so unless you really kind of made the initial conditions so that one point is going towards another and really hitting it, unless you choosing those initial conditions specifically like that, in general, that will never happen. And that's great because you will never hit the divergence exactly in your integration. Now, geometric phase effects turned out to be taken care of because now you don't have anymore the electronic functions that introduce double valuedness because of their nuclear dependence and nuclear coordinate dependence. All right, and then all the problems kind of go away because of that. Now, just to see that indeed this is happening, we looked first at the two Gaussians on the Mexican hat problem. Like we have a conical intersection, cylindrical symmetry, and you put two Gaussians and make them go around the conical intersection so that they meet on the other side. And so the usual adiabatic representation doesn't really introduce the proper destructive interference due to the geometric phase, and because it's missing geometric phase. But now in this moving crude adiabatic representation, we can see that at a later time, we indeed see the destructive interference, and this is like just a density plot. You can see the nodal line appearing here when the two Gaussians actually moving on the other side. There is another actually thing, there's another advantage that we didn't think of initially, but the advantage is just coming from the fact that when we are working with a new representation, we don't need to do some approximations in potential energy surface that we usually do in the normal quantum dynamics. So in normal quantum dynamics in adiabatic representation, we naturally split the Hamiltonian in two parts, the kinetic energy of nuclei and the electronic, right? And when it comes to calculating matrix elements between the basis functions, well, then naturally you integrate out electronic degrees of freedom first, and then you need to integrate Gaussians with essentially potential energy surfaces calculated, right? And then in order to calculate these matrix elements, you need to somehow approximate potential energy surface because you don't know them as analytic functions of the nuclear coordinates, right? So you do some sort of Taylor series approximation and maybe go up to forces, maybe up to Hessian if you really want to do more accurate representation. But usually people stop at the Hessian because then it becomes very expensive. Now with this new representation, we can completely remove potential energy surface as a concept. Why this is possible is because the electronic Hamiltonian at any arbitrary nuclear geometry is not actually the operator for which our wave function, electronic wave functions are eigenstates, because the center of Gaussian may not coincide with the like this big R that we have in electronic Hamiltonian. Now, it becomes more natural actually to split the total Hamiltonian differently without introducing an electronic Hamiltonian. It's more natural to split it completely than the part for the nuclei, which is kinetic energy of the nuclei plus potential energy of the nuclei, then the same for the electrons, and then electron nuclear Coulomb interaction. So what this gives us is when it comes to the calculating the integrals, then we can simply factorize for the nuclear and electronic parts, corresponding parts. And then the only thing that couples everything together is electron nuclear potential. But because in electronic structure, people usually use Gaussian functions, and in the nuclear part, we use Gaussians, this becomes a very mathematically kind of convenient integrals, because there's a lot of machinery already built in order to calculate Coulomb integrals between the Gaussians. And so that different splitting allows us to avoid to introduce the potential energy surfaces and do any and kind of avoid introducing any approximations for those objects. Now, how does this all work? So far, we looked at the very simple model system, but at least this model system has explicit electronic coordinate and explicit nuclear coordinate. We took it as I think it was also used for the exact factorization work by Hardy-Gross, and it's 2D generalization of Shin and Metiu original model. What it has, it has essentially 3 nuclei, which are like a protons with slightly, well, it's like 100 times a lower mass, so it makes things more quantum, right? But 2 protons are frozen, and the whole thing is considered only in 2D. So you have 1 electron, which is an active particle, and 1 proton as an active particle. And then moving in 2D, that's why we needed to modify the Coulomb potential to be a so-called soft Coulomb potential. With all that, turns out you can kind of solve both electronic structure and kind of for every nuclear position of that 1 proton that is unfrozen, and obtain potential energy surface just as a kind of a guiding surfaces. We don't use them really for the simulations because now we don't need them, but they just tell us where the conical intersections are and how many of them are present. So in this model system, there are 2 states which have 2 conical intersections. It's a 2 doublet state, D2, D1. And so in order to see how this all works, we put the 4 wave packets and see the essentially transfer between D2 and D1. So this is adiabatic populations. We can project back to the adiabatic states and see the normal dynamics, how things are going from D2 to D1. And also we can see how the geometric phase effects appear, because there are 2 conical intersections. When you start at D2, right here, there is a 1 wave packet kind of combined out of all the Gaussians. Then it goes around the first intersection. This nodal line builds up because of the geometric phase destructive interference. And then at a later time, when these 2 lobes kind of go around the second intersection, well, 2 destructive interferences kind of essentially result in the constructive interference, and we get back kind of similar wave packet as we started with. So similar processes happening on D1 in parallel, but in D1 we kind of start already with 2 lobes because that's kind of a transition from D1 due to the D2 coupling that creates that. All right, but the same kind of geometric phase effects we see on T1. And that shows that indeed we are capturing all the right physics with that originates from the geometric phase. All right, so to conclude, adiabatic representation is nice in the sense that it it's provided by the electronic structure packages, but it's very problematic for the doing dynamics. And so moving crude adiabatic representation essentially resolves many of these problems. And we were so happy that we jokingly thought about calling it making adiabatic representation great again. It was like just before the election in 2016, but then knowing the results, that joke became not very funny. Anyway, so I think that it has a great potential, this new approach, and it even allows us to remove the approximation from potential energy surfaces that usually needed. And let me acknowledge people who has done all the work. It's mainly Ilya Rybinkin who started this geometric phase considerations in my group. And also most of the work on the moving crude adiabatic representation is done by Loic Joubert-Drial. Now he's in has an independent position in Université Paris Marne-Laval, and these funding agencies, and all of you for your attention. Thank you. I'll be happy to take any questions.
Thank you, Artur. Does anybody have questions? Okay, then my question will be first. So what actual trajectories for Gaussians, which represent vibrational dynamics, are used in the simulations you have shown? You described many options, right, which can be chosen, classical trajectories or kind of variational trajectories. What option did you find the most practical?
Okay, so they have certain advantages and disadvantages. For example, classical movement of Gaussians. The biggest advantage is that you can parallelize, and I think that was done mainly in work of Dmitry Shalashilin. So what they do, you can run many Gaussians, but all in parallel, because for their propagation you don't need to share information between them, right? So you can, if you have like a supercomputer with lots of nodes, you can run them all at the same time, and then you can just kind of calculate what the dynamics of amplitudes will be for those Gaussians, and that requires like gathering the information from all of them and doing that. But that is a relatively easy part, because it doesn't need any electronic structure information. It's already, you already propagated the Gaussians. Now that has one issue, is that it doesn't conserve energy, strictly speaking, unless you have many Gaussians, or they don't interact with each other, like they don't bump to each other. So I think currently we're working on fixing that, because it's an interesting approach where you can do things in parallel. But in all this works, we actually did mostly the quantum propagation of Gaussians, because it just requires fewer Gaussians to solve the problem, and for model systems it's kind of affordable for us. So yeah, to be sure, they have this advantage of more compact representation and than the classical propagation, which require more. Yeah.
Okay, we have more questions. So Caroline, please.
Yeah, so hello, Artur. I wanted to ask whether your Gaussians are frozen or thawed.
They're frozen. Yeah, sorry, I probably didn't mention that. Yeah, we never worked with thawed Gaussians, because yeah, it's known that they have some issues when you kind of go on the surfaces with a negative curvature, and yeah, they start thawing and creating instabilities in dynamics. So we never like really looked carefully into those questions. Just we were staying away from that by freezing the width and having enough of them to represent the wave function, hopefully.
Okay, thanks.
Gerhard, your turn.
Yeah, great talk. I was slightly mystified by the fact that your electronic wave functions, the Born-Oppenheimer states, they don't depend, as you showed, on the capital R anymore, but just on the Q, the center of the Gaussian, right? Now, still, to calculate this object, right? You run your electronic structure code, and it spits out some result. And isn't it that there can be a phase which is now a Q-dependent phase, right, which is essentially arbitrary?
Well, it's not arbitrary in the sense that you have a control, right? So if you start from a point Q0, right, and then start evolving the Gaussian, you can make sure that the Gaussian at the next Q point has the same, or electronic function, sorry, not the Gaussian, but electronic function attached to the Gaussian has a phase that optimizes the overlap or maximizes the overlap. between the previous wave function and the current one. So in that sense, you keep track of phase. You can keep track of phase. Indeed, if the Gaussian goes around, then that electronic function will naturally change the sign because it will acquire the right phase. Now, what happens is, I guess, the coefficients, the amplitudes in front of the Gaussian, they can they can also be a double valued kind of functions of Q because they attach to the same Gaussian. And what we did essentially is we removed necessity for Gaussian to be a double valued function. And that's what I believe is the key to treatment of the geometric phase, if it demystifies somewhat for you.
So do you actually maximize the overlap from one time step to the next? So is that what you're actually doing, or
right. Yes.
Okay,
yes.
Okay. Then I get it. Yeah, thank you.
And that maximization may sound like something that may involve a lot of resources, but in the real arithmetics, maximization is just a switch in sign plus or minus one, just selecting it properly. And we need overlaps in general. Yeah. So. Yeah.
Okay. So this is because usually the output of the electronic structure code is a real valued function. So you just choose the right sign, so to say.
Right. Yeah. So
okay.
Usually it looks at the Slater determinants, and for the largest one, it always makes them positive, and then you just need to hack a little bit and make sure that it's not assigning the arbitrary phase; it assigns.
Okay. Yeah. Thank you.